Now we will formally define vector space. Vector space definition. The set V is called vector space over field F when the vector addition and scalar multiplication satisfy the following properties. Satisfy the following properties. We'll denote some properties related to addition from a, like there are 10 properties that should satisfy in order to we call a vector V as belonging to a vector space defined over field F. So here we will have 10 such axioms, so we'll see one by one. So first axiom under addition rule, we say that if there is a vector x bar and y is another vector, and we consider its vector addition, x bar plus y bar is belonging to this vector space for all x bar and y bar belonging to the same vector space. This property is called, this we call as closure property for vector addition. Let me repeat. Like it is given, considering x is a vector, y is a vector from this vector space V. If we consider to take the addition of these two vectors, the resultant vector will also lie in the same vector space. So this rule says that is nothing but, in other terms, we say it as a closure property for vector addition. So now in the second one, we can write as x bar plus y bar plus z bar is equals to x bar plus y bar plus z bar for every vector x, y, z belong to the vector space V. So what does this rule say is that in for every vector x, y bar belonging to vector space V, it is immaterial to understand whether, if we consider the okay, let me rephrase it like this. It is our least concern if the vectors are the order in which the vectors are getting added up. So this, and this is a very well known property. We say it is an associative property. Associative property for vector addition. In some textbook you will find this associative property. where this is normally we say that it is our least concern with the order in which the vectors get added up. Like in this here you can see first we are adding up to x plus y vector, then we are adding it z, but in the right hand side we can see we will get the same vector if we first consider to add y plus z, and then we'll add it with x. So so this is how this property is defined. So let us go to the third property, A3, where x plus y is same as y plus x for every x and y belonging to the vector space V. This property in some textbook you will find it as a commutative property under vector addition. So here also it says the same thing. It is if you add x plus y, if you interchange the elements also, we are going to get the same vector, same set of vectors, and it is hoped that the resultant vector should lie within the vector space it is defined of a field. So the next property, A4, there is an element 0. There is an element 0 belonging to vector space V such that x plus 0 is equals to x for every x belonging to vector space V. So this property says that for every x that is belonging, like this is the given condition, for every unknown, for every vector x that is belonging to certain vector space V, if there is always if there exists as element 0 vector that is also belonging to the same vector space, and when we consider the addition of those two vectors, the resultant vector will be the vector itself, and by this also we say that the resultant vector lies in the same vector space. So this is one of the properties that should satisfy for vector addition. So the fifth property, A5, for each vector x bar belonging to V, there is an element minus x bar belonging to vector space V such that x plus x minus x should give me a 0 vector. In some textbook, this I think they call it as an existence of an additive inverse. This property normally they consider is an existence of additive inverse. And this property, I think they call it as the existence of an additive identity. Existence of additive identity. These are the 5 axioms related to the vector addition. In the next lecture or module, we can will see the rest 5 axioms related to scalar multiplication that defines the vector space.